Good morning, everyone, and thank you for having me to quickly just discuss what the SKA is and the kind of ICT challenge that we face in the construction, the development of the SKA instrument. I always promise one slide of science, addressing why are we building the SKA. And really it's about trying to develop an understanding of the laws of nature and the laws of physics, because all the matter that we can feel, all the light that we can see, all the heat that we can feel constitutes only 4% of the total energy of the universe. 21% of the stuff called dark matter, so-called because we know it's there, we can see its gravitational effect, but we can't see it. And the rest of the stuff called dark energy. I'm certainly not going to go into detail there. So what is the SKA? So the SKA is an international astronomical community's intent to build a radio astronomy facility 100 times more powerful, more sensitive than anything that has ever been built in history. There are about, probably closer to 20 different governments in the SKA consortium. This is about a slightly outdated slide because it's probably closer to about 70 top research institutions, and those include both academic institutions like the universities of Oxford, Manchester, California Institute of Technology, University of California, Berkeley, but also major companies like IBM and the Tata Institute. And the reason why they're involved is because they see that the technological challenges that are being confronted by the SKA and being solved by participants within the SKA project have significant and widespread commercial benefits. As an example, the supercomputer that we require to process the 400 terabytes per second of information that the instrument is going to produce is something like 200 to 500 times more powerful than any supercomputer that exists today. It's got a proposed construction budget of, this is probably closer to about 2.5 to 3 billion euros. And we hope to have it operational by about 2024. But it's a long-term system development. And this is what the SKA is going to look like. It's really a big DSTV dish. 3,000 of them, 15 meters in diameter. And really, the bigger the better in astronomy. The more dishes you have, the more collecting area you have, and therefore the more sensitive the instrument becomes. And the more sensitive the instrument is, the weaker the signals that you can detect. So we've got about 3,000 of these. Half of them, 1,500 of them, are concentrated in a 5-kilometer core. And really, it is like a big DSTV dish. These dishes aren't made of steel, or certainly the surface at this point probably won't be made of steel, because steel is just too darn expensive. So we look at other types of material composites to develop this dish. One of the interesting concepts we've developed is a plastic dish that you just spray a metallic surface on. These are generating something like a terabyte per second of information, each of these dishes. We not only have dishes, but we also have these things called sparse aperture arrays. And this kind of technology, for those of you in the satellite industry, you take your dish and you've got your LNB or your receiver. You take the receiver off the dish and you put the receiver on the ground and you get rid of the dish. And what that allows you to do is you look at the entire sky all at once, all the time, and you create your dish in software. And so this aperture array is like a cat's eye lens. It allows you to look at the entire sky all at once. And this is why we need this huge supercomputer, because we've got to process each and every single signal coming from each of these receivers. This is just a different type of what's called a dense aperture array as opposed to sparse aperture array. It's a different frequency range. For those RF engineers out there, this instrument is going to be operating from something like 50 to 100 megahertz up to 10 gigahertz in the first phase, and going out to about 35.5 gigs in the second phase. So we've got all our sensitivity by building lots of collecting area. Now what we want is resolution. We want to improve the dots per inch in the image that we produce. And the way we do that is we spread out these stations out to something like 3,000 kilometers from the central core. And we've got to get all of that data back to a central supercomputer. And it's not just about getting the data back, it's about time stamping the data, because what we have to do is we have to phase up all of the data signals that are being received by every single telescope up to something of the order of a picosecond time resolution. And this is the last slide about science. And why we want to build such a huge amount of collecting areas, because we want to detect very weak signals. Because when you build a telescope, it's effectively like building a time machine. Put simply, when you see the sun set, remember the light from the sun takes about 8 minutes to get to us. So every sunset that you look at, the sun actually set 8 minutes ago, and the light is only just reaching us now. When you look up at stars at night, much of the light has taken hundreds, if not thousands of years to reach us. So many of those stars are already dead. We just don't know it yet because the light hasn't got to us. If we build an even more sensitive instrument, what we're able to do is detect signals that have been traveling through the universe for billions of years. And we'll be able to detect signals right here. This is a timeline. The universe is 13 billion years old, or some 13.7 billion years. And we hope to receive signals coming from the very start of the universe. And hopefully in a couple of years' time, I'll be able to take a presentation and show you a snapshot image of the universe at different times in its history to try to study the evolution of it. So some technology facts and figures, which is, gosh, that's 10 minutes already. 5 minutes, sorry. Some technology facts and figures. So the SKA is so named because of the total collecting area. The amount of collecting area is 1 square kilometer. The central supercomputer will have 10 to the 18 floating operations per second. It's an exaflop machine, right? We have to literally, that's something like a couple hundred times more powerful than anything that exists today. On top of that, it needs to be extremely power efficient. But just that supercomputer, assuming the most amazing, remarkable improvements in power efficiency, will still require about 30 megawatts of power to drive, excluding cooling. I'm never impressed by this optical fiber, but sure, we'll use enough optical fiber to wrap twice around the Earth. And I think the diameter of the Earth is something like 40,000, I'm not quite sure, but that's a lot of optical fiber that we will need. The dishes are going to produce, someone at IBM once produced this stat, that the dishes could produce 10 times the global internet traffic at any one time. And all of that is feeding into a single data processor. But that's the dishes where you've got the receiver at one point and you've got the dish. Remember, in the sparse aperture arrays, we're taking the dish away and putting the receiver on the ground and creating the dish in software, which means the aperture arrays will produce 100 times the global internet traffic, current day stats. Enough raw data. So this is like a petaflop machine. I mean, a petabyte, it's going to produce about a petabyte of data every day. Right? So you can imagine that we actually can't spin hard disk drives fast enough to store that data. So we need to process it all in real time. And that's why we have this huge supercomputer, to process it and crunch it down to manageable data chunks. Then what do we do? Well, we've got to get rid of it as quickly as possible. We've got to distribute all of that data to the world's astronomical community, which lie across the globe. This is what the SKA actually looks like in Africa. The bulk of the collecting area is located in the Northern Cape province of South Africa. Each of these dots is about 24 dishes. But there are other locations in African partner countries. So we've got Namibia, Botswana, Zambia, Mozambique, Madagascar, Mauritius, Kenya, and Ghana. Remember, each of those dishes are producing like a terabit per second or terabyte per second data rates. And we've got to get all of that data from every single one of these dots to a big central supercomputer right there in the middle. So we require about 216 gigabit per second links from every single one of these stations to the central core. Going closer into South Africa, interestingly enough, this is a population density map of South Africa. And clearly when the government drew up the provincial borders, they drew a line around where everyone lived and called the rest of the Northern Cape, because less than 2% of South Africa's population live in the Northern Cape. And as a result of low population density, you have a low presence of radio frequency interference, because radio's telescope is very sensitive to RF. So the distribution of telecommunication services, specifically in the areas around the Northern Cape Province, can't be relied on for RF as a signal delivery, as a delivery mechanism. And what we went and built some very sensitive receivers, radio receivers, 3 of them, drove around the country. And for those of you RF engineers out there, you might recognize this as a spectral plot. Some radio signals, FM radio signals down there, US military satellite signals, right in the middle of our VHF broadcasting, television broadcasting band, SABC2 and only SABC2, which broadcasts to about 5,000 people and 20,000 sheep, I suppose. And some Vodacom and MTN signals up there. But it's pretty fantastic for use for a radio telescope. All this clean spectrum over here will be used by the SKA. We also have an act to protect that area. It's called the Astronomy Geographic Advantage Act. It empowers the minister to promulgate regulations and declarations that will ensure protection of the SKA. And that's a picture of our protected areas, about 500 to 600 kilometers across. Some data requirements. Well, the data rates from each receptor. So each of those stations, those dots that you saw in the configuration, will require sustained 216 gigabits per second links to that central supercomputer. Don't have to worry about that. These aperture arrays, the sparse and the dense, something like, 33 terabit per second sustained to our central supercomputer. From that data processor, it's first going to a data processor, I should point out. And this data processor is made up of completely customized hardware that we developed in-house, which is, I suppose, a telecommunications engineer's dream, to have some of the equipment that we produced. Out of this data processor, what it does is it explodes the data rate to something like 400 terabits per second. And that's going streaming from the data processor into the supercomputer. So all of that is all co-located in the Karoo, where the supercomputer will process all of the data in real time, crunch it down to manageable bits, and then send it to the rest of the world. This 100 gigabit per second data link is required to each and every single science center that is distributed around the world. And we'll probably look about 5 or 6 different centers around the world. So we have to get it out of South Africa to the rest of the world and across to the rest of Africa. Of course, we're helped by the proliferation of undersea cables that are now connecting Africa to the rest of the world. And having a look at terrestrial fiber optic infrastructure. Certainly we need to be able to use terrestrial links from all of our partner countries, maybe not Madagascar, but certainly the rest, to get our data to the core. And just a picture of where our core site is in relation to existing broadband Africa long distance network. And a quick update, which I'll use my last minute. So for those of you who are interested, we've just commissioned the first 7 dishes of the SKA. It was considered to be an engineering and scientific prototype, but it is under international demand for usage by the international community. We're busy doing the civil works for Meerkat, which is the first 64 dishes to the SKA. That will be integrated into the first phase of SKA, which is 215 dishes to be commissioned in 2016. And we're entering into what is called a pre-construction engineering program. Our international SKA office advertised a request for proposals, which is open to the international community to become involved in the SKA and develop a large part of the technologies that will be required. Just as an aside, what is also quite interesting is another program we're doing with the proliferation of terrestrial and undersea submarine fiber optic infrastructure. Satellite telecommunications dishes, large-scale satellite, 30-meter class telecommunication dishes, are slowly becoming redundant. And so what we've done is we've identified quite a few of them in Africa, and we're actually turning them into radio telescopes. So here's one, which is operated by Vodafone in Ghana, and there's its cousin in Italy. And that's an operational radio astronomy facility. And so we just started work with our Ghanaian team to convert this into a radio telescope. This is some of the equipment that we produce. This is called Roach, stands for Reconfigurable Open Architecture something harder. Oh, there it is. At the bottom, reconfigurable open architecture. And effectively, this is a sort of next generation reconfigurable data processing platform. The original idea was conceived at University of California at Berkeley, but then we joined the program, fixed all of the bugs, redesigned the second version, and we're busy redesigning the third version in Cape Town. And for that, you can, for those telecoms people out there, you can do I guess an FFT analysis, real-time analysis on 1 gigahertz of bandwidth. And it's used around the world at this point in time. And I'm happy to take questions. Thank you very much.